So this video is about simple machines. Simple machines have been used for millennia, way back to ancient civilizations like ancient Chinese, ancient Egyptians, ancient Native Americans. All of them started using very, very simple machines like inclined planes and wedges and levers. And so today we're going to take a look at the different simple machines and what they do. So a simple machine is a device that helps make work easier. And so it doesn't make work easier by reducing the work. Instead, it's going to do one of four things. It's going to change where the force is applied. So if you're using something like a lever, maybe you're applying the force in the middle instead of at the end. So it changes where the force is applied. They can change the direction of a force. For instance, a pulley, your goal is to lift something up. So rather than apply a force in the upward direction, a pulley allows you to apply a force in the downward direction. It makes it easier for you. So they can change direction of the force. They can change the size of the force, so you can use less force. A lever actually allows you to use less force to lift something than if you didn't have that. But when you change the size of the force, you actually change the distance. You can't just change one or the other. When you change the size of the force, you have to change the distance. That's how you're going to be able to manage that changing of the size of the force. So when you have a smaller force, you're actually increasing the distance that the simple machine is moving over. And we have 6 different types of simple machines. They are the lever, the wheel and axle, the pulley, the inclined plane, and the screw. There are 3 types of levers that we're going to be talking about today and 2 types of pulleys. For everything else, there's just that one single type with different examples of them. So let's take a look at the levers first. A lever is a rigid bar that rotates around a fixed point called the fulcrum. So that point where it rotates, where it seesaws over, is called the fulcrum. Most often our levers are going to be straight, but they don't have to. They could be a curved bar. But we're always going to have things like an effort, which is the applied force, a load, the object that we're moving, or the resistance force, and that fulcrum. So label the parts of the lever on your notes page. Please be sure to locate the resistance arm, which is the distance from the load to the fulcrum, and the effort arm, which is the distance from the effort or the force that's applied to the fulcrum. Please pause this video so you can write these down. There are 3 classes of levers. I would like you to write down on your paper, I didn't include a spot, but next to where it says there are 3 classes of levers in that open space near your picture, write down that saying FLE 1, 2, 3. Right here, this FLE 1, 2, 3. That's going to be really important in determining the class. So we're going to see that the class of the lever is determined by what's in the center and what's on the edges of that. So F is going to stand for fulcrum, load is the L, effort is the E, and 1, 2, and 3 are our different classes. So let's take a look at our first class lever. These are the different pictures of them. So in a first class lever, the fulcrum is located in the center or between the effort and the resistance or our load. So first class levers, you should have fulcrum is between the load and the effort. Is between the load and the effort. That's what you should write on your paper. The fulcrum is between the load and the effort. So some examples are going to be crowbars, scissors, which are actually a compound machine, but they do have first class levers included, seesaws. Those are all examples of first class levers. And these are going to change the direction of the force. I'm going to show you a picture of a first class lever here in a moment. And I would like for you to draw that on your paper, but please be aware that a first class lever changes the direction of the force, not necessarily the amount of force. So here's a picture of a first class lever. I'd like for you to draw this on your paper. Please notice that the fulcrum is not in the exact middle. However, it is located in between our effort and our resistance or load. So the fulcrum is in the center between the effort and the load. Please make sure you've paused the video and drawn this picture on your paper. Now let's take a look at a second class lever. So we're on the part of the saying that is the L2. So we did the fulcrum for our first class lever. Now we're on the L for our second class lever. So FLE, 1, 2, 3. So now we're on the load, which is our second class lever. So the second class lever, the load, is between the fulcrum and the effort. So on your paper, you should actually have the load is between the effort and the fulcrum. The load is between the effort and the fulcrum. So some examples are going to be nutcrackers, wheelbarrows, doors. The door that you open to get into your classroom or your bedroom, those are actually second class levers because the load is the door itself. Our fulcrum is the hinges and the effort is the door handle, which you'll notice is on the opposite side of the hinges. And these guys are going to change the size of the force, but not the direction. So if you wanted to move the load to the left, you would have to push to the left. Or if you wanted to move the load up, you'd have to pull the lever up. So it changes the size, but not the direction of the force. So let's take a look at a picture of this. And I'd like for you to draw this on your paper. So go ahead and pause the video so that you can draw this on your paper. Notice that we have the fulcrum on the end, our effort on the opposite end, and our load in the middle. Does your fulcrum have to be on the left? No, your fulcrum can be on the right, but then your effort needs to switch sides, because the load needs to be in the center. So again, notice our load is in the center, our effort's on one end, and our fulcrum's on the opposite end. And now we're on the third part of our simple machines, of our levers. So a third class lever is the effort. So there's our E, and we've got our 3. So we've already done the fulcrum is in the center of our first class lever. The load is in the center of our second class lever. And now the effort is going to be in the center of our third class lever. FLE, 1, 2, 3. Fulcrum is in the center of our first class lever. Load is in the center of our second class lever. Effort is in the center of our third class lever. FLE, 1, 2, 3. Fulcrum, load, effort, first class, second class, third class. So we're on the third class lever. So at this point you should have effort is in the center of your simple machine. So on your paper, you should have, for third class levers, the effort is between the load and the fulcrum. The effort is between the load and the fulcrum. So some examples are going to be tweezers, hammers, shovels, rakes, brooms. Excuse me, those are all examples of third class levers. So let's take a look. Oh, I'm sorry, let me talk about this last bullet down here. It changes the distance and therefore the size of the force required to move the object. So you're actually moving the object over a larger distance, but it's allowing you to do so with less force because of the lever. So let's take a look at this and I'll explain how it shows a hammer. So draw this on your paper. Make sure that you've paused the video so that you can do so. Notice that your fulcrum is on one end and your load is on the other end. So our effort is somewhere in between these two. Maybe it's in the middle, maybe it's closer to the load, maybe it's closer to the fulcrum, but you'll see that the effort is in between the fulcrum and the load. So this is a hammer because if you think about it, our hammerhead is the thing that we're moving. So your hammerhead would be here. Your hand, which provides the effort or that force, is in the middle, and the fulcrum is the end of the hammer. That's the point that it pivots around. Pivot points, fulcrums, do not have to be on the ground or on a surface. They can be in the air. This is why a hammer or a shovel or a rake or a broom are all third class levers. Your hands, which are not at the end, are providing the effort. The fulcrum is always the end of the handle, and the load is the thing you're trying to move. So maybe that's the hammer head, or it's the rake head, or it's the shovel head, or it's the broom head, but it's always the thing you're trying to move. So those are all examples of third class levers. This one is probably the hardest one to understand, so please be sure to see a teacher to ask for more clarification of how a broom or a hammer is a third class lever. So those are our levers. Now let's take a look at a wheel and axle. So a wheel and axle is really pretty simple. They're two concentric circles, meaning circles that are attached and are similar in size. Similar in shape, but different sizes. You have a larger wheel and usually a smaller axle or a shaft that serves as the axle. There are some benefits to this. When you turn the wheel, you actually apply a smaller force over a larger distance, which means you end up with a big force on this axle because it's traveling a much smaller radius. So you apply more force. So that's why we see examples of screwdrivers as our wheel and axles, because when you turn the larger wheel, you're applying a force over a larger distance. So this in turn applies a larger force to your axle. So you're applying more force to the axle because you're applying a smaller force over a larger distance on your wheel. So we've got screwdrivers are examples, faucet handles, so the things that turn on the water, as long as they're not the long ones, if they're the round ones, that's a wheel and axle. A round doorknob is a wheel and axle. So anytime you have something that's circular shape that turns, that you're applying a force to get turned, it's probably a wheel and axle.